All right, here we go with Thermodynamics 2, numbers 12 all the way through 27. And this would be number 12. How's that? Pretty good? There we go. Alright, looks like actually, yeah, 12 and 13 are going to be close together because it's the same topic. So, an empty container is filled with helium to a pressure of P at temperature T. Neon, which has atoms that are 5 times more massive than those of helium, is then added to the container until the new pressure in the container is 2P at the same temperature. Same temperature. Okay. The ratio of the average speed of the helium atoms to the average speed of the neon atoms. So, important point here is same temperature. So, and I guess it doesn't really matter, but everything in the container is at the same temperature, obviously. So, they all have the same average kinetic energy. But a neon is just 5 times more massive, so kinetic energy of neon is 1/2 velocity of neon, well, mass of neon. You know what, let's do this. Instead of writing mass of neon, let's write, here, let's do this first. Let's do the helium first. So let's do the kinetic energy of the helium is equal to the mass of the helium, called m, and the velocity of the helium squared. Kinetic energy of the neon, which by the way, like I said, it's the same kinetic energy because they're at the same temperature, is 1/2 5m's, right? 5 times more massive, times the velocity of the neon squared. But these two are the same kinetic energy. Same average kinetic energy there. So really you have 1/2 m v helium squared equals 1/2 5m v neon squared. And they want us to compare the ratio of helium atom speed. So they want helium. When I'm done solving this thing, what I want is I'm going to want to have, I'll put it off to the side here, I want V helium over V neon. That'll be the ratio, helium to neon. Helium to neon, and so on and so forth. So let's leave this here. Obviously the 1/2s and the m's go away. Leave V squared, V helium squared here, divide by 5. No, sorry, divide by V neon squared. So I have V speed of helium atom squared divided by the speed of the neon squared equals 5. So I don't want the ratio of their squares, I want the ratio of them, so I'm going to square root both sides. So the ratio is going to be square root of 5 to 1 when I'm done that, because this will be VH over VN will be equal to the square root of 5, which is same as square root of 5 over 1. So I would go with C as my right answer on that one. Since I haven't done this one before, let's just double check. Yep, good. All right, now this one, the ratio of the number of helium atoms in the container to the number of neon atoms in the container. Interesting. Okay, so we had, I think this is an ideal gas law. P V N R T. N is the number of moles of things. So we had a certain pressure. This is all about the fact that if you look up at the problem, they said that the pressure was doubled. So the T stays the same. We went from N, a number of moles of helium, and then we added neon, so we increased N without increasing the temperature. We didn't change the volume of the container. All we did was add it until the pressure was doubled. So I put a 2 PV over here, which means I have to put a 2 over here. I must have doubled the number of things. Now, so careful. Don't go 2 to 1. Oh, good. They don't have 2 to 1 over there. If you double the number of things, so if you had, we're just going to keep it simple. If I had 3 moles of helium, if I double that, I add 3 moles of something. That must be the neon. So they must be the same amount. So I would go with 1 to 1 for 13. All right. So far, so good. Batting 1,000. That was 13 as well. Now we're on to 14. I'm leaving this up there longer so that when you scroll through it, you might see it better. Okay. 3 different gas samples that have the same number of molecules and are at room temperature are kept at different pressures. They haven't said anything about the volume yet, have they? A lab technician has determined that, well, if they're at the same temperature, the volumes have to be different, right? A lab technician has determined the molecular mass of each gas and recorded the pressure and molecular mass of each sample in the table below. Pressure, all right. Links the density of the gas samples. This ought to be interesting. All right. Well, let's go with first thing. PV because nRT would tell me that temperatures are the same, pressures are different. That means the number of molecules is the same. So all this side stays as a constant. So different pressure means different volume. All right. Wait a second. Volume shows up in density, doesn't it? Density is mass divided by volume. So maybe, I've done this problem before, but I'm thinking I figure out what's going on with V for each one of these, and I'll use the mass this as a substitute for this, and we'll see which one's bigger. So it may not be an actual unit or something, but it doesn't matter. So here, what would be the volume? So this is all constant. So if I take, like this one has a pressure of 1, let's see, so this one's volume would be, well, we could look at it like this, nRT over 1. I could divide both sides by the P. So the volume in every case is nRT over P. That would be nRT over 1, nRT over 12, and nRT over 6. That would be an expression for each of their volumes. Okay. So what about their densities? Well, let's use this. So for gas X. Anyway, for gas X, I would have a density of, we'll go with 2, right? Because it's all the same unit. So, and realize it shouldn't probably be, well, the units would probably wouldn't make any sense, but we're just looking at quantitatively here. Over nRT over 6, which is really 12 over nRT. Y, using the same sort of thing, is going to be, its density is going to be 4 over nRT over 12. 4 times 12 is 48, so that would be 48 nRT. And then similar process for Z is going to have 40. It's going to have a 1 on the bottom, so it's going to be 40 over nRT for Z. So the density of X is this, the density of Y, the density of Z is going to be 40 over nRT. So based on what I'm seeing here, remember the nRT is the same for all of them. I'm going with y is the biggest, then z, and then x. So I would go with this. Let's see if I'm right, because I have not seen this problem before, ever. Yes, I got it right. So what's important here is this. I didn't really know the approach to this problem. So this is an important point. So hopefully you're looking at this problem. I did not know the approach to this problem. I have not seen it before. I was making it up as I go along. So what do you do when you make it up as you go along? What is the point? Well, first of all, start with what you know. Contemplate what you know. Well, I know these are all constant based on what I read here, so if P changes, V's got to change. Now, here's where my experience helps. It was pretty quick for me to realize, well, V is arranged in, or is involved in density, so, wait, if I go find some V's and I got some masses, I think I can do density. But it might take you a little longer. But you don't have to actually know. I did not know that was what I was going to do when I wrote this down. I was just looking at, look, this is what seems to make sense. They give me pressure. They told me the same number of molecules, so that would indicate N is important or involved, or at least they had to make sure that I knew it was the same. And I let it develop from there. So while having some experience here helps, yes, but this is something you can do. Some folks get into this idea where if they don't see the answer immediately, they panic and they don't start it at all. And so I would highly recommend just start with what you know. Hopefully you make a right guess. If you reached in here and started pulling out, average kinetic energy is 3/2 Boltzmann's constant times temperature, you'd have been barking up the wrong tree. But then I would have asked you, at what point did kinetic velocity and kinetic energy come up in here? It's not there. So this wouldn't be the right choice to start with what you know. This contains the stuff that you know. So, all right, moving on. 15. Two blocks of steel. The first has a mass of 1 kilogram, the second has a mass of 2 kilograms, are in thermal equilibrium with a third block of aluminum. Aluminum, mass 2 kilograms, that has a temperature of 400 K. What are the respective temperatures of the first and second steel blocks? Thermal equilibrium? Okay. Thermal equilibrium just means the same temperature, I believe. I believe you're in thermal equilibrium when you're at, because if you have different temperatures, you have different kinetic energies, so energy would flow from the higher energy to the lower until there's a balance. So I'm going with this. I think this is a ridiculously easy one. All right, don't overthink it. Thermal equilibrium is just a fancy word for same temp. 16. Two containers, each holding a different gas, are brought into thermal contact. The gas atoms in container X have twice the mass and half the average speed as the gas in container Y. Which of the following best describes the energy transfer by thermal conduction? Okay, so basically, here's what I'm thinking. We know, hopefully what you know, is that thermal energy will go from the higher temperature, right? It always goes from the object with the higher temperature to the lower. That's the way it flows. Cold is not a thing. It doesn't flow. It's just the energy goes from higher temperature to lower until they're at the same temperature. Well, you're like, but they don't tell us about temperature. Well, they kind of do. Remember, go with what you know. They're talking about temperature and speed. What do you know that involves temperature and speed? There's not that many formulas in thermodynamics. So I know that the average kinetic energy is 3/2 Boltzmann's constant times temperature. But I know average kinetic energy is 1/2 the mass of the gas times its average velocity, or RMS velocity, or speed really, squared. So whichever one has the bigger average kinetic energy has the bigger temperature. All right. So one of them has twice the mass, but half the average speed. All right, so this is, yet again, if this is not sunken in for you by now, I don't know what to do. The square, it's all about trying to trip you up with that square. See, they want you to believe that, in a way, they want you to make the mistake of, some of them want you to, but the mistake they're trying to see if you will make is that twice the mass, half the speed, they'll cancel out. But they won't, because in kinetic energy, velocity matters more. So half of this is going to really come down to 1/4 of the kinetic energy. So one of them has this kinetic energy. The one that's different than that has its kinetic energy would be twice the mass, but of half of the speed. So these are not the same thing. This is gas number 1 is gas number 2. Or let's see, what's the X? This would technically be container X according to their labeling, and this is container Y. And so when I square this, I get a 4 in the bottom. Okay, now this 2 does cancel out one of those, but I have 1/2 m VRMS squared, and this 2 cancels out one of the 2. This becomes a 4, but then again, so I end up with a 2 underneath there. So this one has the higher temperature than this. So Y has the higher temperature. So energy will flow from Y to X, if I'm getting this right. Hopefully I didn't switch up X and Y. There is a net energy transfer from Y to X. I would go with B. And then he looks over with some trepidation. Yes, I am correct. So it's definitely, go with what you know. It's got kinetic energy. When they give you mass and speed, it's kinetic energy. So whichever one has the higher kinetic energy is where the energy is going to go start from, and whichever one has the lower kinetic energy is where it's going to end. You want to be careful. Yes, doubling the mass would double the kinetic energy, but having the speed produces a fourthing. I don't know if that's a word. A quartering? Maybe we should do that. Of the kinetic energy. So if you double it and you cut it down by 1/4, that's cutting in half. And that's what we ended up with here. So this one had half the kinetic energy of the original. And all we needed to know is, it really doesn't matter how much more, that X had more energy. So, sorry, that Y had more energy, and that's why it transferred from Y to X. 17. A lot of words in this question. I seem to remember doing this one before and not loving it, but we'll see. My recollections get fuzzy. Here we go. 17. Right. Student designs an experiment intended to determine the thermal conductivity of an unknown material. 2 15-centimeter long bars with the same cross-sectional area are joined together as shown in the figure above. The bar on the left is made of copper. The bar on the right is made of unknown material. The left and right ends of the 2-bar combination are maintained at 40 and 20 degrees Celsius. So the left side is at 40 degrees Celsius, and this is at 20 degrees Celsius, respectively. And the bars reach equilibrium. The student then measures the temperature T along the bars and produces the data shown in the graph, where x0 is the left end and 30 centimeters is the right end. Okay. The experimental uncertainty of the data is negligible. Which of the following can the student conclude about K sub C, the thermal conductivity of copper, compared with the K of this? thermal conductivity of the unknown material? Well, all right. Whew. That's a bizarre question, but hey, we'll give it a shot. So first, where are we going to start? Well, there's only one equation that does thermal conductivity. It's not one that we use often, but it's Q over delta, or delta Q over delta T, the rate at which heat was moved through these things, equals, I guess they use K sub whatever. So K, they use K, maybe, yeah, the conductivity. I think the equation she uses rho, but that doesn't matter. The area, increasing the area would change it, and L. And the delta T is in the top. The bigger the delta change in temperature, the more faster energy will flow. So I don't have that equation memorized per se. I just can picture, like, the thicker these are, the easier it is for heat to flow. The longer it is, the harder it is to make it across. The bigger the temperature difference, that would make sense. If it's like 4,000 degrees and 20 degrees, heat's just going to flow. I guess it's just going to push it faster, so to speak. So, all right. I'm not sure how much of this is going to apply here at all, to be honest with you. This, once again, I'm writing down what I know. I'm looking at it, I'm wondering, I don't know what the heck see, I'm not sure. If everything's in equilibrium, there's got to be heat flowing still. But yeah, time isn't involved here, so I'm not crazy about this. We'll see. Unless, what if we solve each one? What if we solve this for K? Delta Q over delta T times L divided by A and delta T equals K. Cross-sectional areas are the same. Time would be the same for both of them. Change in temperature is the same on either end. Well, let's see. I got a couple options. Maybe delta T isn't the same. So the next thought that comes to me is halfway through, this temperature is, I'm guessing it's about 35 degrees. So the delta T for copper is really 40 to 35. The delta T for the unknown material, it gets this half of the thing, is 35 down to, what is it, 20. So delta T for the unknown is 15 degrees, whereas delta T for the copper is just 5 degrees. If it's in equilibrium, okay, so I'm going to go with this. If it's in equilibrium, I'm assuming that the rate at which the heat is being transferred is the same for both. I'm assuming that the overall rate is the same for both. That delta Q over delta T, what if that was the same for both? Areas are the same. Their delta T's are not the same. Their lengths are the same. So whichever one has the, okay, so delta T would be in the bottom here, right? So whichever one has the bigger delta T has the smaller K value. All right. Now, the bit of a stretch I made here is I'm not 100% confident in saying that the rate at which the heat is flowing through copper and through this are the same right now. But I'm pretty confident because of this, the temperature drop isn't the same. So this is probably forced to be the same by the whole system working out so that the temperature changes, that the temperature drop from here to here is less than the temperature one here to here. So, based on what I've just said, if all this else is the same, if K for the copper is basically some constant over a 5-degree change, and the K for the unknown is the same constant over a delta T of 15, that I would say that the K for copper is 3 times larger than the K for the other, right? Because if I multiply that by 3, I mean, you could look at the ratio if you wanted, right? You could go, whoops, yeah, you could go Kc over K unknown, which would be constant over 5 divided by constant over 15. You move that so you can see it. Now, when you're done that, the ratio would be 15 over 5, which is 3, so 3 to 1. Let's see. No, we don't even need to know an actual number, so maybe part of my reasoning is wrong, but what the heck. I would still say that copper would be more than the unknown. I would go with C. Oh boy. I'm not feeling super confident about this, but we'll see. Number 17. Yes, I got it right. I remember doing that last year, I think, and just botching it horribly. So there you go. I'm improving. I'm becoming a better physics person. And let's face it, that's all you can do in life. You don't want to become a better person. You just want to become a better physics person. Treating people nice, that doesn't matter. Getting physics problems right? Now that's important. Two objects heated to different temperatures. The objects are then placed in thermal contact with each other and insulated from their surroundings. After equilibrium is reached, which of the following must be true? All right, thermal equilibrium we looked at in an earlier problem. Definitely the temperatures have to be the same. The amount of thermal energy lost by one object equals that gained by the other. I think that might... right, because they're going to have the same internal energy. That one's tempting to say it's right. I know this one's true. The total energy of the insulated system has not changed. Once again, I would say that's true too. I swear I'm not looking over at the answers, right? So I'm going to make myself a guess. I have this sneaking suspicion I might be wrong on this one, but I'm going to say E. I'm going to say that all of them are true. Certainly one is true. So I could definitely rule out this, and I could rule out this. So I can get it down to 3. Logically, both of these seem right to me. Maybe I'm missing something in a physics sense. It's time to look. Let's just... 18 is in fact E. Okay, so I am correct in my conservation of energy here. Actually, in a way, if you agree that this is true, which I think is easier to agree to, that the total energy of the insulated system hasn't changed because it didn't leave, right? And it wasn't turned into another form. If that's the case, then the energy lost by one has to be equal to the energy gained by the other. So this here, the second one, is really a consequence of the third. So I guess once if I look at these and I'm like 3 I think is true, I wouldn't choose 1 and 3, which isn't even an option. I would have to choose all of them. I'd have to choose all of them because I think this one is a consequence of that. There you go. Two samples of an ideal gas in separate containers have the same number of molecules and the same temperature, but the molecular mass is greater than which of the following correctly compares the average once again. All right, so we got mass and speed. All right, so they have same temperature, so they have the same kinetic energy. And the gases and the average force the gases exert on their respective containers. All right, we'll come back to that one. Although, yeah, no, we will, because you know what we're going to do? this, okay, so from a while ago in one of the earlier problems, if you've been, keeping up, the force is going to come from change in momentum. But we need to know, let's figure out what's going on with the speed. All right, so we know this is the way this one's going to process out. We're going to say kinetic energies of X and Y have to be the same, the average kinetic energies, because they're at the same temperature. From that, the speeds, all we know is that the masses, the mass of X is more than the mass of Y, so that means the speed of Y has to be more than the speed of X. Let me see if I get that right. Mass is greater for X, so its speed is less, but it's not less by the same proportion. Kinetic energy, right? So this is the tricky part. The speed, right now all I can say is the speed is less here. Ooh. Hold on. All right. So what I can say right now is this: is that the velocity of the X ones is less than the velocity of the Y. I can say that for sure. Why? Once again, if they have to have the same kinetic energies, if the mass of if this one's bigger mass, then the velocity unit square has to be less. So I got that. Now, you know what? I don't think I need to go change in momentum, because something occurred to me a moment ago. PV and RT. Now, two samples in separate containers. The only thing I don't know is whether the volumes are the same or not. That's the only thing that concerns me here. Is they don't say the containers are identical. They just say they contain the same number and they're at the same temperature. But they don't tell me this V. Because if they said they were in identical containers, then they would have to have identical pressures. But they don't say that. They just say the containers are separate and they have the same number of molecules. But they are at the same temperature and they have the same amount of these. My other alternative a little bit ago was going back to change in momentum. Every time one of these hits a wall and comes off again, the momentum is 2mv for both of them. So it would be 2mxvx for that one. That's your change in momentum over a certain amount of time. Right? Change in momentum. Yeah, no, that would equal the force divided by a certain amount of time. Let me look at the answers, because part of me says you can't answer without V, but let me look at it. All right. So it's an option. We'll see. So I'm all right with the average speed is greater for Y. So I got it down to these two. Based on what I've just discussed, I'm going to go with I don't know the volume, because that would affect the time, not the time of collisions, but the number of collisions that they would make. So maybe I have to think on that one, but I'm going to go with, I would go with D. I'd be wrong here. Eventually I'm going to be wrong at some point. I just don't see enough right now to get this, to come to that conclusion. I know it has more, they have more velocity, but the other one has more mass, so momentum might just be a wash. And if there's a way to determine if it is or not, I'm missing it. So I would go with D on this one. Let's see if I'm right. Find out. This is 19. 19 is in fact D. Okay, so I'm not completely as clueless as I'd hoped. These questions are tough. Ones where one of the options is you can't determine it. I mean, if you're struggling if you can and you're just struggling, you're likely to be like, I can't determine it. So, yeah, they can be tough. But we certainly should have gotten down to a 50-50. And I know, this year's AP exam isn't going to be a multiple choice part to it, but still, we should be again to at least that as an indicator that we're on the right track. All right, number 20. Sample of an ideal gas is taken through the cycle that we see here, A, B, C, back to A. All right, what is the change in internal energy for the process BC? Okay, I almost was going to say, I thought they were going to ask us what the change in internal energy is for the whole cycle. And anytime you come back to where you started, this is the same internal energy. There's no change. But they went from just B to C. All right, well, what's the internal energy here at B? Well, that's going to be 4,000 times 0.5. That's going to be 2,000. What's the internal energy here? It's 2,000 times, well, it's going to be 2,000. So if the internal energy here is 2,000 and this is 2,000, then the change for that process would be 0. Let's take a look. So I would go with C as my answer for number 20. And I would be correct. So just straight, always double check. If they give you numbers, it's just straight as calculating the PV here, which is the internal energy. And so it's doing the same thing here. '21. Gas is taken from state I to state F along the two-step process shown. What is the ratio of T final to T initial if the temperature of state F... Oh, what's okay? So they want a ratio of the temperature. Well, that's just going to be a ratio of the... Once again, let's find the internal energies here. Because the internal energy here is 8,000. And the internal energy here is 4,000. And and they want final to initial. So internal energy, which is PV, is also nRT. So the PV, P final, V final, produces an internal energy which would be an indicator of the final temperature. P initial times V initial, which is 4,000, is nRT initial. So if I just take their two, this is their internal energy, so is this. I calculated it using PV, but it's also a number that would represent this. So all I have to do is take the final internal energy, 8,000, over the initial, 4,000. That would equal nRT final over nRT initial. But the nRs are going to go away. And so this is the ratio. It's 2 to 1. The temperature at the final, I don't know what that temperature is, but that's because I don't know the amount of moles, but the temperature at this spot is twice as large as the temperature here because the internal energy is twice as large. I would go with D. All right. Still rolling. 22. The average speed of molecules in a certain sample of gas, there you go, is V. The absolute temperatures of the gas is T. If the average speed of the gas is doubled, what is the new... Oh, come on. Come on. Come on, you got this. This is like, it's like a softball, right? This is like, come on, you got this. You should hit this one out of the park. Because average kinetic energy is equal to 3 halves, Boltzmann's constant times temperature. Kinetic energy, of course, is 1/2 mv RMS, the average velocity or average speed squared. So if you go from v to double v, when you square it, that's going to come out to be a factor of 4. So you have 4 times the kinetic energy, 4 times the temperature. I would say A. Yes. Should have been a relatively easy one for you. I mean, I don't mean to be judge, right? If it was hard, it was hard. It's fine. But that's just trying to catch you on the squaring there. All right. This is going to be 23. It's a little funky because the diagram is on one page and the way I copied it. So there we go. Okay. So we have this diagram, which is going with this problem. A very hot gas composed of equal numbers of positive... Oh, wait a second. We've seen this question before. Well, let's see. We've seen a similar situation. Positive ions is in a closed, thermally insulated container and is at thermal equilibrium T0. The figure above represents the initial distribution of the ions. A strong, uniform electric field directed towards the bottom of the page is now created in and around the container, and it's allowed to reach it. Which of the following represents a... Oh, come on. Really? This is an electricity question, isn't it? That's all it is. They're saying, all right, we put a field that is directed towards the bottom, I believe. All right. Field's this way. So the electric field points in the direction a positive charge will get pushed. So I would expect positives to be at the bottom and negatives to be at the top. No. No. I like this one. I like C. Yeah. Now, there's enough thermal energy. They're going to, they're not going to all be lined up at the bottom. But just to make sure, that's 23. Yeah, it is C. So I would say this, right? That's more of an electricity question than a thermal question. (24). All right. Getting there. 24. Certain quantity of an ideal gas, initially at temperature T sub 0, pressure P sub 0, and volume V sub 0, is compressed to 1/2 its initial volume, as shown above. The process may be adiabatic. Process 1 is an adiabat. Now I can't remember how to spell it. Adiabatic. Process 2, I'm guessing, is isothermal. Yep. And this one's constant pressure. All right. Which of the following is true about the final temperatures of the gas? Well, all right. Well, here. So, come on now. The final temperature of the gas really just depends on this position. I don't really care how they got there. I did all this writing for nothing. Because the final temperature is all dependent on their position on this graph. This guy is P times the same P times a smaller V. This has identical, it's isothermic, so it should have, that's the only maybe useful, that should have exactly the same internal energy, same temperature as TO, same internal energy as well. This, well, it's the same volume, but at an even higher pressure than this one, so this has to be the largest. So I would say this is the highest temperature for 1, the next is 2, it's the same, and 3 is actually a lower temperature. Its greatest for process 1 would be, it's not the same for process 1 and 2. No, so I would say A. I would say A. 24A. Yep, I would say A. 25. Oh, okay, now that it's the same drawing, so we might as well keep it here. So 25, hold on. 25. No. So same drawing. Says, which of the following is true about the mechanical work done on the gas? Alright, so every one of these is going to the left. That's work done on the gas. And we know that the key fact here is its area under the curve. So which of these has the most work done under the curve? That looks like it's 1 again, doesn't it? So I would go 1 again. Let's see. It's greatest for process 1. I still think I would go with A. And I would be right. Alright, but that's just an area under deal. $26. Almost there. $26. Which of the following statements is not a correct assumption of the classical model of an ideal gas? All right. Molecules are in random motion. They are. Check. The volume of the molecules is negligible compared to the volume occupied by the gas. In other words, they're really, really tiny. I think that's one of the assumptions. The molecules obey Newton's laws of motion. A good indicator that that's true is classical model. All right, so I'm going to go with that one. Not as confident. I think I found it. I found our one. Whoop, whoop. This is an alert. All right. The collisions between the molecules are inelastic. Wait. They're not. They're elastic. They're supposed to bounce off completely. Like they don't stick to each other at all. That's the assumption. So this is not true. The collisions would be elastic. They bounce off without any sticking whatsoever. That may not be actually true in some cases, but many cases or all. In fact, I don't think a pure elastic collision is a theoretical, but it's an assumption based on this model. So the only appreciable forces on the molecules are those that occur during collisions, right? So in other words, ignore gravity and that sort of thing. That really, for them, the collisions are all that really matter. That's also an assumption. So there. If they had said elastic, they'd all been, I think, assumptions. So there you go. 27. Which of the following will occur if the average speed of the gas molecules in a closed rigid container is increased? Let's not even look at the answers right now. Average speed. You increase the average speed. So that means you increase the average kinetic energy, which means you increase the temperature. But you do that in a closed rigid container. Well, that means PV equals nRT. You didn't change the number of molecules. You don't change the constant. You can't change volume. So if you raise the temperature by increasing the average speed, you have to raise the pressure. So I would say pressure goes up, temperature goes up. Those are my answers, and I don't even know what the selections are. All right, density of the gas will increase. It will decrease. I'm not sure about that. Density of the pressure. Oh, pressure of the gas will increase. I like that one. Do I get two of these? No, temperature. Yeah, I'm thinking there's not two answers, right? No, and there isn't really. The other one isn't in here. So, yep, So yes, the temperature would go up, but you're supposed to then use the ideal gas law and come up with the fact that the pressure would also go up. They don't even give you temperature going up as an option. Right. All right, I think I'm done.